This is the last of 3 videos about the notion of limit. It is not a formal definition yet. I am only presenting the geometric intuition behind the concept of limit. In the first video, I presented examples of functions that had a limit, in the second, of limits that did not exist, and in this third video, I will look at side limits. Here is my last example, example 5. Is the function g defined by the equation g of x equals x squared plus x over the absolute value of x. G of 0 is undefined, so I'm going to study whether this function has a limit at 0 or not. When x is very close to 0, is g of x very close to a number? The best way to deal with an absolute value is probably to break it into cases, depending on whether the thing inside the absolute value is positive or negative. In this case, when x is greater than 0, then the absolute value of x is simply x, and I can simplify the expression for g of x. It will be x times x plus 1 over x that simplifies to x plus 1. And similarly, when x is less than 0, the absolute value of x is minus x, and g of x simplifies as x times x plus 1 over minus x, or simply minus x minus 1. So these are the two expressions for g, and each one of them is the equation of a line. I recognize them, so I know what the graph is going to look like, something like this. Now that I have the graph, let's forget about the algebra and let's look at the graph only. If x is very close to 0, is g of x very close to one single number? I'm afraid not. I'm going to have to say the limit does not exist, because when x is close to 0, g of x is sometimes close to 1 and sometimes close to minus 1. It should be one single number for the limit to exist, so this limit does not exist. But it does not exist in a very specific, controlled way, because when x is close to 0, g of x is very close to either 1 or minus 1, depending on whether x is positive or negative. So let's give a name to this phenomenon. I'm going to say that the limit as x approaches 0 on the right is 1. And I'm going to denote it with this equation, where I have put a plus as a superscript of the 0. And I'm going to say that the limit as s approaches 0 on the left is minus 1. And I'm going to denote it with this equation, where I have put a minus as a superscript of the 0. What does this mean? Well, roughly speaking, it means that if x is very close to 0 but greater, then g of x is very close to 1. And if x is very close to 0 but smaller, then g of x is very close to minus 1. So the limit does not exist because g of x is not close to one single number, but does not exist in this very specific way. And I'm going to call these two objects the side limits. To conclude, let's summarize all the types of examples I've seen in these 3 videos of different ways that a function may or may not have a limit. The limit of a function at a point may or may not exist. When we say the limit exists, this means it is a single number. If x is very close to a but not a, then f of x is very close to L. The typical example will look like the one in this graph, where it's a nice function that at the point simply has a hole. Notice that it doesn't matter whether the function is not defined at the point in question, or it is defined and has, so to speak, the wrong value, or it is defined with the right value. All those count as the limit existing. If this doesn't happen, we say that the limit does not exist. And the limit may not exist in different ways. Perhaps it doesn't exist because the limit is infinity. The function grows arbitrarily large near this point, like the one in this graph. Or perhaps it is minus infinity. Or perhaps the two side limits exist, but they have different values, like in this case. Or perhaps something else, like the one in this graph. In this case, the limit does not exist because near the point, the function oscillates widely. All those are different ways in which the limit doesn't exist, because as x approaches a, f of x is not approaching one single number.